Thank you, AKADIMOS, for inviting me for online class. Today I am going to discuss thermodynamics, the basic part of science, physics as well as chemistry. Before going to discuss different laws of thermodynamics, first you have to know some fundamental term associated with thermodynamics. You know thermodynamics based on 4 different laws. First law of thermodynamics, that is the total energy is conserved. If A form of energy converted to B and C form, then A equals to B plus C. And from second law of thermodynamics, you will get idea about in which direction a phenomena is possible. Any phenomena in science, that may be chemical or physical, is nothing but change of energy. And from third law of thermodynamics, that is basically statistical mechanics, from there you will get idea about the absolute energy value. And zeroth law of thermodynamics, from there you will get idea of temperature. Now some basic term associated with thermodynamics. First you have to know system. That system is a part of the universe where we are focusing or from where we are taking data and we are doing analysis. That part may be divided from the rest part of the universe by imaginary world or real world. That is our system, and this system plus rest part of the universe is called surrounding, and this system plus surrounding equals to universe. That universe. Now in this system are of 3 types. One is called open system. Open system means between system and surrounding there occurs exchange of mass. That means number of moles, they are variable. Mass associated with number of moles. Number of moles change not equals to 0, as well as there occurs energy change. Here energy generally thermal energy. That is open system. All natural phenomena occurs in open system, and maximum number of variables you will get in open system. Then closed system, their number of moles is not variable. Matter exchange will not occur. That means number of moles change is 0, but there occurs energy change between system and surrounding. And isolated system, number of variables here reduces since number of moles here constant. Isolated system, completely isolated from the rest part of the universe. Isolated system, no matter exchange, as well as there occurs no energy exchange. And minimum variable you will get in isolated system, and you can easily analyze isolated system since there are no relation with the surrounding. Then most difficult to analyze the open system since number of variables there come maximum. Now our syllabus basically based on the closed system. Next part that you have to know, that is the properties of the system. That properties of system, properties are of 2 types. One is called extensive property, and extensive property are those properties which are depends on amount of matter present in the system. Like extensive property, volume, amount of matter if increases then volume increases, number of moles, mass itself, you can say mass dependent property. Like heat capacity depends on mass of the substance present in the system. Any energy functions, any energies are extensive property. You will get in thermodynamics internal energy U, that is extensive property. Enthalpy, extensive property denoted by H. These 2 energy function you will get from first law of thermodynamics. Remember, these energies are thermal energy at different condition. From second law of thermodynamics you will get Helmholtz free energy, extensive property. Gibbs free energy, extensive property. Entropy, extensive property. All are extensive property. That means depends on amount of matter present in the system. That means that depends on number of moles. Intensive property are not depends on amount of matter present in the system, like density. Density of anything not depends on amount of matter, concentration, and all molar property, molar volume, molar heat capacity, molar internal energy, molar enthalpy, any molar properties are intensive properties, since there you have fixed the amount of matter present in the system, that is the 1 mole. That's why any molar properties are intensive properties. Other than molar properties like electrode potential, also intensive property, and refractive index, intensive property. These are intensive property, not depends on number of moles. Then you have to know state of a thermodynamic system. Before going to explain a state of a thermodynamic system, you have to know in thermodynamics, basically we have most available energy in the universe, that is the thermal energy, and that thermal energy is associated as chemical energy. If you burn any fuel, you will get automatically thermal energy. But most useful energy today, that is the mechanical and electrical energy. Now you have to think how this most available energy, thermal, you will do convert to most useful mechanical and electrical energy. Here in thermodynamics, we will discuss mainly about how thermal energy converted to mechanical energy. Just think, you take some gaseous substance, that is the working substance of thermodynamic systems, and put a movable piston and give heat, supply thermal energy, and due to thermal energy the gaseous system temperature increases, and according to Charles the volume increases. The piston will goes upward, that means it will convert it to mechanical work, and the energy converter here, the working substance of the thermodynamic system, that is the gas. Actually in our syllabus up to JEE Advanced, working substance will take gas, and there we will consider it will behaves like ideal. Real gas we don't have in our syllabus, remember. That means the working system is gas, and thermodynamic system is the gaseous system, and in gaseous system the each and every property of the gaseous system depends on 4 variables: pressure, volume, temperature, and number of moles. These are called state variable. State of a thermodynamic system defined by these 4 fundamental state variable, and all energy functions of the thermodynamic system depends on this 4 variable. And this n is fixed for closed system. If it is constant for closed system, then the variables becomes 3, and you will get a mathematical restriction between these 3 variable. Since we are considering it will behaves like ideal, it is constant, and there is a restriction between these 3 variable. That means among these 3 variable, 2 are independent variable and the third one is dependent variable. That's why any thermodynamic energy function, you can express function of either temperature, pressure, or function of temperature and volume, or PV. Generally we will take TP or TV. Number of moles here constant for closed system. These are called fundamental state variables. Next part that you have to know, that is the path dependent. Actually in thermodynamics you will get 2 different variables. Variables are energy or pressure, volume, temperature, number of moles. 2 types of variable. One is called state variables. State variables or state functions, you can say state variables, and another one you will get path dependent variable. Path dependent variables or functions, you can say variables. Actually state variables, that means depends on initial state and final state only, like displacement depends on initial and final. The minimum length is the displacement, but distance is path dependent. If you do follow different path, then distance will be the different. That is the path dependent variable. Like velocity velocity variable, you know, that is the state variable, and the speed is path dependent variable. So in thermodynamics also you will get some state variable, some path dependent variable. State variables are generally pressure, initial pressure P1, final pressure P2, then the change of pressure is P2 minus P1. Not depends on how you change P1 from P2. Volume, temperature, number of moles, internal energy, enthalpy, Helmholtz free energy, entropy, Gibbs free energy, all are state functions or state variables, depends on initial and final state. Whereas the path dependent variable, that will depends on which path you are following to change from initial to final state. Here you will get Q, heat change, and work done, W. These two are path dependent variable. Now the question is, what is path in thermodynamics? What is path? Actually here in thermodynamics, the change is the fundamental variable change, that is pressure change, volume change, temperature change, number of moles change. That is the change in thermodynamics. Actually path here, number of steps you are following for particular change. Number of steps. For example, you are going from, you have taken here gas, the initial state, let P1, V1, constant temperature I am considering here, and you want to go P2, V2, that is the final state. And there you can do follow one step, that is the one path. If you do follow two number of steps, then the path you got there different path. Three number of steps, different path. That means number of steps different means different path. And also remember sequence of steps. Actually path in thermodynamics is nothing but the number of steps and sequence of steps. Sequence of steps, for example, you are changing P1 T1 to P2 T2. First you changed P1 to P2, then T1 to T2. That is one sequence. Another sequence, first you change T1 to T2, then P1 to P2. That means sequence is different. If some properties depends on path, that means depends on number of steps and depends on sequence, then they are path dependent variable. And remember, the path dependent variable are not exactly differentiable. Only the state variables are exactly differentiable. There you can take a mathematical restriction. Cyclic integral means initial state and final state is same. You can consider it is a cyclic process. And any property thermodynamics X, its dx infinite, similarly small, perfectly differential. If it is, then in the cyclic integral the dx you will get 0. Then x is perfectly differentiable, or dx is perfectly differentiable, and x is a state function. X here, if a state function, then cyclic integral of dx, there you will get 0, state function. X is a state function and dx is perfectly differentiable. And sequence of step, for example, it will depends on temperature and pressure. Then del 2x, del t, del p means first you change their pressure, then temperature. Now I do change the sequence, del 2x, del p, del t. Here I have changed first temperature, then pressure. If due to change of sequence, the change of x is same, then it is a state function. These two are the condition of the state variable or state function. This is called Euler's reciprocal relation. If they are not equal, then it is path dependent variable. If this is not 0, then it is path dependent variable. Remember Q, heat. Heat is a general term. In thermodynamics, all energy functions are thermal energy or heat energy. This is heat energy. This is also thermal energy per Kelvin. This is also thermal energy. But these are thermal energy at a different condition. That means these are narrow functions. When this thermal energy at different conditions, see, they surprisingly become state variable. but Q general is a path dependent variable. Later you will see W generally path dependent, that means it will depends on number of steps, but there you will get some cases where W also becomes a state variable at different conditions, like W adiabatic is a state function, W reversible is a state function. Next, you have to know the term thermodynamic equilibrium. Actually, in thermodynamics, two types: thermodynamic equilibrium. Thermodynamic equilibrium, you know what is equilibrium? When variables are time invariant, then it is called equilibrium. Here thermodynamic variables when time invariant, then thermodynamic equilibrium is reached. Here the thermodynamic variables means pressure, volume, temperature, number of moles and the associated energy. Actually thermodynamics are two types: reversible thermodynamics and irreversible thermodynamics. In our syllabus we have reversible thermodynamics, that means their time variable is absent. In our syllabus no time variable you will get, but when it is irreversible thermodynamics, there you have to take time variable. That means a system when reached equilibrium, then we will analyze the thermodynamic parameter at that equilibrium condition. Next, work. Important term, that is work. Actually, in thermodynamics, work mainly pressure volume work. Here, pressure volume work, that is mechanical work actually. Mechanical work. And you know, work is force into displacement along the direction of force. Here actually mechanical work, pressure, force by area, volume area into length, pressure, volume, and sign convention. Remember in chemistry, there is minus P external pressure, that is opposing pressure, that is the final pressure, into volume change. The sign convention I will discuss why here minus. But in physics, the sign convention W is equal to P external into volume change. Here the positive. Actually remember why here negative. Here actually in chemistry we will use the IUPAC sign convention of work. For example, here P1, V1 initial state, final state is P2, V2. That means you have decreased pressure P2 and initial pressure P1. The volume increases to V2 and the driving force here P1 and the opposing force or external force or pressure is P2. Here W is equal to, will write according to IUPAC or chemistry convention, minus P2 into V2 minus V1. Now why the minus sign? Actually IUPAC convention always with respect to system. When you are doing expansion, that means there you have to apply thrust or force on the piston. That is called work done by the system. Remember, expansion means work done by the system. Expansion means if system will do work V2 greater than V1, by which energy of the system decreases, that's why you will get negative. You know, expansion V2 greater than V1, automatically from this expression you will get W negative, and the physical significance of W negative is the decrease of energy of system. Actually IUPAC convention always with respect to system. But in physics, that expansion work you will get positive. When system will do work and you will get some positive work from the system or machine, then it is positive. That's why expansion work here positive. And if you do contraction, there you have to apply thrust on the piston, that is called work done on the system. That means contraction means work done on the system. Any contraction means work done on the system. And if you do work on the system, what is nothing but energy, which will increases energy of the system. That's why automatically from the expression you will get the positive work, since they are for contraction V2 less than V1. This is the difference between the sign convention of work in IUPAC convention, that is chemistry, and in physics. Another term is heat. You know heat is a form of energy, and all energy has the natural trend to convert to heat energy, and heat energy can partially convert to another form of energy. And you know the result of heat is the change of temperature or change of phase. But the important part in the basic of thermodynamics, that is different types of process associated in thermodynamics. Different types of process. First, remember cyclic process. Cyclic process. Cyclic process means your initial state, this one. This is your final state. Let it is A, B, and from B you reverse back to the initial state. That is the cyclic process. And you know this cyclic process is highly important. From engine you will get continuously some positive work by continuous supply of fuel. That means you are supplying continuously thermal energy, and continuously you are getting useful work from the engine, and that engine always work by cyclic manner. That's why cyclic process is important. And all state functions, the net change of the state function, you will get here 0, since you know state variable depends on initial and final state. Since here initial and final state is same, change of state variables are 0, but the change of path dependent variables are not 0, remember. Another process, that is isothermal. Very important, you know Boyle's law, its background experiment is isothermal in closed system. You know in Boyle's law, number of moles is constant, temperature is constant. Number of moles constant means closed system, temperature constant means isothermal. Only the variable is there, pressure and volume. The isothermal process, isothermal process, their constant temperature, that means change of temperature is 0. Now I will discuss. For example, you are doing Boyle's experiment. You are decreasing pressure, there occurs volume increase. V1 initial pressure, final pressure P2 V2. Now, if this change will occur expansion, or you can take as example contraction. Here I am taking expansion, initial P1 V1, final P2 V2, and this expansion I told you work done by the system. And if system will do work, then its energy decreases. And you know energy decrease is nothing but thermal energy decreases. That means temperature will fall. But there you have to maintain constant temperature. That means there you have to absorb heat from the surrounding. By taking immediate heat from the surrounding, you can maintain constant temperature. The number of steps there you have to take infinite. That means reversible change. That part I will discuss later. That means here I want to say here Q is variable. Q here heat exchange between system and surrounding. Any isothermal process, if there occurs pressure volume change, then there must occur thermal energy change between system and surrounding. Next, adiabatic process. Number 3, adiabatic process. Adiabatic means there occurs no change of heat, no exchange of heat between the system and surrounding. thermally insulated wall. System is thermally insulated, covered by thermally insulated wall. No heat exchange will occurs between system and surrounding. Now, if there occurs no heat exchange between system and surrounding, and parallelly if there occurs pressure volume change, then work done by the system or on the system, by which energy of the system increase or decrease. If energy exchange will not occur, then energy increases or decreases, means temperature increases or decreases. That means their temperature must be variable. Any adiabatic process phenomena, pressure volume variable means temperature must be variable. Now the fourth number of process is isobaric, very simple. Pressure is constant, and if pressure is constant, you are supplying heat, then volume is variable, that is isobaric. And isochoric, volume is constant, you are supplying heat, then pressure is variable or pressure increases. If you extract heat, pressure decreases. But the important process is polytropic process. Polytropic, remember, it is most important in physics actually. Polytropic process. What is polytropic process? Actually, polytropic process is the process, its fundamental definition is throughout the change. Pressure may be variable, volume variable, everything is variable, but at any instant, their heat capacity remains constant. At any instant, their heat capacity remains constant. Heat capacity, amount of heat required to increase the temperature by 1 Kelvin, or amount of heat you have to extract from the system to decrease the temperature by 1 Kelvin. At any instant, the heat capacity of the system is constant. That means initial heat capacity of the system and final heat capacity of the system is constant. Then it is called polytropic process. But it is very difficult to realize. You can simplify if there occurs pressure volume change, and this change of pressure volume will follow a fixed mathematical restriction, PV to the power n is equal to constant. If the change will follow this mathematical restriction at any instant, then it must be polytropic. In chemistry, we have little bit polytropic phenomena, but that polytropic phenomena are very simple. There you will get pressure by volume ratio at any instant is constant, or you can say PV to the power -1 is equal to constant. That means in chemistry problem generally came or will come that there I will take n is equal to -1. This is also a polytropic phenomena. Now the most important part in types of process, that is reversible and irreversible process. Most important, reversible and irreversible process. A reversible, parallelly I will discuss. A reversible and irreversible process. Irreversible process. Actually, see, here I have taken gas, initial state, let P1, P1. I am taking temperature constant. The final state is P2, V2. It is a gross change and considerable change. P2, V2. You have decreased pressure to P2, volume increases to V2. Actually, the definition of the reversible change. If final state, here the final state is P2, V2, reverse back to the initial state. Reverse back to the initial state without applying any external stress. That means without applying any external force. If P2, V2 reverse back to the P1, V1, then it is reversible. But it is impossible. How it will come back to the P1, V1 without applying anything? It is impossible. Then what is the reversible process? See, if I do split, if I change this P1, V1 to this, that means here I am writing here the initial pressure was P1, and in the first step I have decreased pressure P1 minus dP. Parallelly, volume will be increased to V1 plus infinitesimally small dV. This dP is mathematically tends to 0, but practically it is minimum. Minimum decrease of pressure. Then there will be a minimum increase of volume. And if you give time, you can consider this step is a reversible step. Since dP tends to 0, automatically dV tends to 0 mathematically. Then in the next step, you know this is the opposing pressure. Next step, again decrease. It was P1 minus dP, now decrease P1 minus 2 dP. Automatically volume increases to V1 plus 2 dV. And this dV, dP mathematically tends to 0. Practically they are minimum. By this way, reach your destination final P2, P2. Final is P2, final pressure, and before it is dP. Similarly, volume finally you have reached V2 and the before one step, that is V2 minus dV. This is your final destination. From initial state to final state, mathematically there you have to consider infinite number of steps theoretically, and it will take theoretically infinite time. Since in each step there you have to give time to reach the equilibrium. Although each step are not real equilibrium, that's why they are called quasi-equilibrium. Now, practically what it is? Practically, if dP minimum, dV minimum, then P1 to P2 practically, since you know thermodynamics is a real science, it has no exception, it comes from the direct human experience. Practically it is the maximum number of steps. That means when you are going from P1, V1 to P2, V2, if you follow their maximum number of steps, then you can consider it as a reversible change or reversible process. Now see, when you are going from P1, V1 to P2, V2, this is the external pressure. This is one step, and there occurs expansion against constant external pressure P2. So when expansion or contraction occurs against constant pressure, then it is irreversible. But reversible, see, the opposing pressure in the first step P1 minus dP, second step P1 minus 2 dP, and finally P2. That means their opposing pressure is variable. You can say if there occurs expansion or contraction against variable external pressure, then it is reversible, and variability theoretically there will do consider it is a continuous variable. Volume change also continuous, and if I consider it is an isothermal process, and here I have taken expansion, and in each step little bit thermal energy decreases of the system, since you know expansion is work done by the system. That means in the first step let initial temperature was T, and in the first step decreases by a dt. Since this work done is infinitesimally small, temperature decreases dt, and if your wall is perfectly thermal conductor, and if you give time, immediate it will take heat from the surrounding by dq amount, and it will reach T. By this way, we will do maintain constant temperature throughout the change, and in each step it will take by dq amount of heat. Now think, reversible process is a continuous process. All variables are continuous since fundamental variables are continuous and associated energy variables are continuous. Reversible expansion or contraction occurs against variable external pressure, and reversible change always occurs through maximum number of steps. Remember, maximum number of steps, and for a finite change there the maximum number of steps is a single value. For example, P1, P1 to P2, P2, let their maximum number of steps is 100. If you do follow 100 number of steps, then the change is reversible, and if it is 1 to 99 number of steps, then you will do consider it is an irreversible phenomena. Irreversible expansion or contraction occurs against constant external pressure. And another thing you have to remember, all reversible variable are continuous and state variable. Although Q is a path dependent function, variable, but remember Q reversible is a state variable. Although W is a path dependent variable, but W reversible is a state function. All reversible variables are continuous and state variables. And if you don't follow the maximum number of steps, then it is irreversible. One thing I want to mention here, that is, this reversible and irreversible term is important only with respect to system. With respect to surrounding, any kinds of change with respect to our phenomena is reversible. You know, surrounding is the huge part with respect to system. Any kinds of heat change will do change the temperature of the surrounding is infinitesimal. For example, if I do supply 100 calorie of heat in the system, there you will get a huge change of or gross change of temperature of the system, that is irreversible. Infinitesimal, anything change is reversible. But that same amount of 100 calorie heat, if you supply to the surrounding, there occurs no significant change of the temperature of the surrounding. That means with respect to our phenomena, any change with respect to surrounding is reversible. That reversible, irreversible term is important only with respect to system. Associated work done later I will discuss in the first law of thermodynamics when we will derive the expression of work for different types of process. Now the last part of the basic fundamental part of thermodynamics. Actually, in first law of thermodynamics, there you will get a term internal energy. This is called internal energy, denoted by U. Actually, its definition, a system by virtue of its existence. That means a system, if exists, it must be associated some amount of energy. And you know energy due to motion. That means anything exists, it must have motion, it must have energy. That is the internal energy. Now you have to know what kinds of motion associated with internal energy. Remember, internal energy associated with the minimum energy associated motion in molecule, that you know, that is the translational energy. Then if I write here according to increasing order of energy, slightly more energy required for rotational motion of the molecule. Energy due to rotational motion. Always energy due to motion. Remember, motion you can observe directly, energy you can't observe. Now, little bit higher energy, that is the vibrational motion. Energy due to vibrational motion. All are associated with internal energy. More higher energy, that is electronic motion. Electronic motion, you know, electron will jump from one energy level to another energy level. That motion associated with internal energy. And nucleus, you know, mass too much higher than electron, its associated motion energy is more than electronic motion, that is called nuclear motion, energy due to nuclear motion. This 1, 2, 3, 4, 5 I have written here according to increasing order of energy. All these 5 motions are included in internal energy, and this type of motion also you will get in rest molecule with respect to us. And another energy associated with whole molecular motion. Whole molecular motion. A molecule is in motion, its associated energy, you know, kinetic energy. That means kinetic energy of molecules associated with internal energy. But one thing I want to mention here, when the molecules are in motion, then all these 5 motions associated energy are included in kinetic energy. That means you are considering kinetic energy, don't you have to consider this. And the last part of energy associated with internal energy, that is energy due to intermolecular attraction or repulsion. Repulsion is negligible, you know, repulsion is very short range force. That is called intermolecular interaction potential. But for ideal gas, you know, this part is 0. Since you know for ideal gas there are no intermolecular interaction between the molecules. You for closed system, if I don't consider the number of moles for closed system, then you generally function of volume and temperature. You know, temperature increases, kinetic energy increases, U increases. This is general for real and ideal. General. But for ideal gas, remember, ideal gas, our syllabus basically ideal gas, you only function of temperature. Now the question will arise, why it will not depend on volume for ideal gas? You know, volume variable here arise just to express the intermolecular attraction or repulsion. You know, any kinds of attraction or repulsion inversely proportional to R to the power n. If I do consider van der Waals, then it is R to the power 7. The volume increases, that means R increases, attraction decreases, and volume decrease means R decrease, attraction increases, and you know attraction increase means energy decreases. That's why an internal energy function of volume if there are attraction or repulsion, and that is applicable only for real gas. For ideal gas this part is 0, that's why it will not depend on volume, only function of temperature. That's why for ideal gas, when thermodynamic system containing ideal gas, any process associated isothermal process, their internal energy change always you will get 0. Internal energy change only depends on initial and final temperature, not depends on other variable like pressure and volume. I think you got idea about the fundamental part associated with thermodynamics, and this has important application in first law, second law, and the next part of the thermodynamics. Thank you.